Lecture 12, Binary Stars and Measuring Stellar Mass. So the last couple of lectures we've spent trying to squeeze as much information as we can out of stellar spectra. And we've fortunately discovered that we can do quite a lot. And in particular, we've talked about how we can find stellar surface temperatures, pressures, and in the past we've been able to calculate distances using things like parallax. And so we kind of wrapped up the last lecture by looking at an example of luminosity and seeing how we can disentangle, things like distance and temperature, distance and brightness and luminosity from one another. Today we're going to take another step forward and consider binary stars and how they can be useful in measuring the stellar mass. Fortunately, it turns out that observations currently indicate that the majority of stars do belong to multiple star systems, mostly binary, sometimes tertiary star systems with 3 stars. There, of course, are isolated, just stars left by themselves in the universe. Our sun is a prime example. So in that case, we're kind of up a creek and we can't directly measure the mass, at least not as easily. But fortunately, as I said, a lot of stars, most stars have nearby stellar partners, and we're going to start off today by seeing how we can exploit that fact to measure stellar masses. So let's dig in. So it turns out, despite the hopeful introduction that I've given you, that measuring masses of stars is much more difficult than getting its temperature and luminosity. So that's the bad news. But having said that, let me actually tell you what I mean by mass, right? It's a term that you're probably familiar with. And it's, to give a not terribly scientific definition, it's a measure of how much stuff is in the star, okay? To be a little bit more precise, if you like precision, it is the inertia, it's a measure of an object's inertia to accelerations. But unfortunately, one of the reasons that it's a challenge to measure something's mass is that some stars are very dense and others are not. The density of stars varies wildly, and we'll see some of that as the course goes on, in particular in the context of the life cycle of the star. We'll see the density of the star changes over its lifetime. So as a result, knowing the physical size of the star, which is something that we do have hope of measuring, as we kind of saw at the end of the last lecture, that doesn't tell you anything as far as the mass of the star goes. It may give you a hint, but it certainly does not give you the end of the story. And so it's not enough to know how big a star is to know its mass. To know its mass, we really need to see how does it respond to forces. And that kind of gives us an indication of why this lecture has the title that it does. Because if we're going to measure something's mass, we need a force to be exerted on it, right? And we need to see how does this object sort of respond to that force. Because that's what mass is. Again, mass is a measure of an object's inertia, or its resistance to acceleration in the face of force. And the only forces large enough to exert any significant influence over something as massive as a star is gravitation. And so if we're going to measure a star's mass, we need something nearby that exerts a very strong gravitational force on it. And guess what can do that? Another star. So that's why we have this two not obviously connected concepts of binary stars and measuring stellar masses put together in a single lecture here, because realistically, the easiest way, the best chance we have of measuring a stellar mass is if we have another stellar mass nearby. So to restate that, in order to measure mass, we have to look at that star's gravitational influence on nearby objects. Okay, so we've talked, it's been several weeks now, so I hope you still remember that we have talked about Newton's law of gravitation and Kepler's laws of planetary motion, and they describe how orbits are caused by gravity and what those orbits are like and what their properties are. So if we can find 2 stars that orbit each other, we can measure the properties of their orbits and we can determine the masses. And so that's going to be the main plan here. So binary stars are not very creatively named. It just means a 2-star system. And when you have 2 stars, they orbit a common center of mass. Okay, So the concept of a center of mass may be one that you have encountered before, maybe not, and we're going to talk about it in some detail here in what follows. But just a couple of examples here, and I don't think the animation will work in the video, but so I won't play it here for you. But I certainly invite you to pause me and go to this URL and take a look at it, because I think it's useful to help understand how these binary systems actually work in practice. On the left, we've got a situation where we have two equal mass stars, and in that case, the center of mass is the geometric center as well, which is just the midpoint between them. And so what will happen in that case is these two stars will just orbit. They will constantly stay on opposite sides of the midpoint, and they'll just orbit, forever, as far as we're concerned. But as you might imagine, in practice, most binary systems do not consist of two stars that have exactly the same mass. And so the middle case is one in which one of the stars is much more massive than the other. And in that case, the center of mass is much closer to the massive star. And in this case, it even lies within that other one of the stars, within a more massive star. And so both stars will still orbit the center of mass. But what that means is that the large mass is going in a very small orbit. It's just kind of turning around a point. I mean, in fact, as I mentioned, the center of mass here is actually inside the surface of this massive star. And so it is orbiting, but it's just kind of turning around the point, kind of near its surface. Whereas the lower mass star is orbiting at a much larger radius. And so colloquially, we would often say that the low mass star is orbiting the high mass star here. But it's actually crucial to know that in principle, both of them are orbiting, and the point they're orbiting is their common center of mass. You can also have more sort of complicated situations where the center of mass is sort of indicated here by the cross, but because of the way that the stars formed, they actually are orbiting kind of in a complex sort of situation, as is shown here, where the two elliptical orbits are kind of offset relative to one another. So they're both orbiting the common center of mass in elliptical orbits, as Kepler's laws sort of indicate that they have to. But this orbit is a fair amount more complicated. And again, that's just a result of how those stars formed. And so we'll talk in a little bit more detail as the course goes on about stellar formation and how this kind of thing can happen. We're not going to be worried about too many of the details here. But the point is that binary stars always orbit the common center of mass. Each star orbits the center of mass in elliptical orbits. But the details of what that looks like will differ depending upon the mass of each star and the initial conditions under which those stars formed. So I've used this term center of mass several times now. So what is the center of mass? So one way of helping to illustrate it is just to imagine putting these two stars on a massive balance beam. The center of mass then is the point at which you need to put the pivot in order for these two things to balance, right? So if these two stars are equal, just like when you were on the playground, if you had a twin brother or sister and you both got on either end of a seesaw, then you would exactly balance, right? And for our purposes, what that means is the center of mass is exactly at the midpoint between the two of you. But if you've got an older brother on the left and a younger brother on the right, well, now the younger brother is going to have to sit farther out on the seesaw in order to balance, effectively, right? And so that's just another way of saying the center of mass is closer to your big brother, right? It's closer to the more massive object. Okay, so the term center of mass really is just what it sounds like. It's saying, where is the average position of these masses? Okay, so in other words, if you had to say, I've got one mass here on the left, I've got one mass here on the right, on average, where is the mass located? Well, it's going to be, on average, located closer to the more massive object, right? And that's that's the qualitative description of this concept. It plays a very fundamental role in calculations of gravitational behavior in orbits. And since we're talking about the gravitational behavior in orbits of binary stars here, we've got to talk about it. But the center of mass is just the average position of the mass, or where would you need to put this pivot in order to balance these two stars. So, to make it a little bit more concrete, imagine a situation where you have a larger mass which is 3 times as large as the lighter mass. Well, the center of mass then will be some distance d1 from the big mass, some distance d2 from the small mass. As you might expect, if mass 1 is 3 times as large as mass 2, then d2 will be 3 times as large as d1. Okay, so in other words, the center of mass will be 3 times as far away from the light mass as it is from the heavy mass. And obviously, if we change this 3 to a 7, then d2 would be equal to 7d1. Okay, so it really is. It's in many ways the center of mass is a common sense sort of concept. But as with any common sense concept, there are plenty of ways that you can trip yourself up and overthink it. But this is what it is. Center of mass, it's the pivot point. It's the balance point, and so if you make an object more massive, then the balance point moves closer to that object. So now that we are experts in the concept of center of mass, how can we actually use these orbits of binary star systems to determine the mass of the stars? And again, so there's a great embedded YouTube video here in the slides. I don't think that it will work in the video, so I won't play it here for you. But you can download the slides standalone, the version of the slides without me droning on, and you can take a look there, or you can go to the URL indicated here on the bottom of the slide. And the important thing here, which is really illustrated nicely in the video, is that as the binary star system orbits. And in this case, we've got sort of 2 different mass stars. You got a relatively large mass star in a relatively small orbit, and then you've got a relatively low mass star in a correspondingly large orbit, both orbiting around the center of mass. And what you'll observe when you watch the video is that as these stars orbit, the observed spectrum shifts a little bit. And it's because sometimes these stars, as they orbit, sometimes they're moving towards the Earth in their orbit, which means the spectrum will be blue shifted a little bit. If you go remember our discussion about Doppler shifting, when an object is moving towards you, its spectrum gets blue shifted. But when it completes that part of the orbit, and now it turns around and it starts moving away from the Earth, well, the spectrum will be red shifted. And it will keep doing that over time. So if we keep watching this star spectrum, we'll see the spectrum change. It'll be blue shifted, and then it'll kind of turn around and be red shifted for a while, and then it'll turn around and be blue shifted for a while again. And by observing those changes in the spectrum, we can determine what its orbital period is, how long it takes to orbit. And by looking at both spectra, we can then calculate the mass. So it's pretty cool. The details are, as always in astrophysics, there's plenty of math in the details. If you're interested in that, as always, I'm happy to talk about it. But for us, that's going to be enough. So to summarize what was said on the last slide, the first step in measuring the stellar mass using a binary star system is our ability to measure the velocity of the stars in their orbits from the Doppler shift of their absorption lines again. So everything is coming from the stellar spectra. We've got 2 combined stellar spectra that we're observing. And they're going to be red shifted as the star moves away from us, and blue shifted as it moves towards us. And by measuring how much that spectrum is red shifted or blue shifted, we're going to be able to determine the star's velocity. And in turn, that velocity information will allow us to determine the nature of these elliptical orbits, how big they are, how big the 2 orbits are, and that will be correlated to the masses through the center of mass. The more massive star, as we saw on this sort of the teeter-totter example, is always closer to the center of mass, and as a result, it has a smaller orbit. In contrast, the lower mass star is farther away from the center of mass and has a larger orbit. The larger the orbit, the faster the star will be moving through its orbit, and the more that spectrum will be Doppler shifted. This particular type of binary star system is something that we call a spectroscopic binary. Again, not very creative. It just means it's a binary star system that we can observe the distinction between, well, we can observe the distinction between these two stars. We can see their combined spectra, and we can observe the Doppler shifting of those spectra as they continue in their orbits. But, as is often the case in any sort of classification, there are several other types of binary star systems as well. So one is known as a visual binary, which just means that the stars happen to be near enough to Earth that we can actually watch their motion visually over time and see that they're orbiting one another. So there's nothing fundamental about a visual binary. It just happens to be one that's close enough to Earth that the telescopes we have now can observe it. And so, of course, there are visual binaries now that were not visual binaries or would not have been called visual binaries in the past because our technology wasn't good enough to observe them yet. And there may be binary star systems that we don't call visual binary star systems yet because our technology hasn't advanced to the point that it will in the future. So, so again, it's nothing fundamental from a physics perspective. It doesn't make it a fundamentally different type of star system. But it's useful because to the extent that we're stuck here on Earth observing, what we can observe, it's useful to distinguish between star systems that we actually can visually see our binary star systems and those that we can't. A second type of binary star system is what we call an eclipsing binary. And this is a binary star system that happens to be oriented in such a way, the orbits of those stars happen to be oriented in such a way that the stars pass in front of and behind one another over time. And the reason that that's useful for us, or makes a difference, is that the intensity of the star's light, the combined two star systems light that reaches Earth, will vary over time in a way that looks kind of like this. So, as I mentioned, typically one of the stars will be more massive than the other. And so there will be times where both stars are visible from Earth just because, of where those two stars are in their orbit. And when that's the case, then we're getting the full, the maximum intensity possible from each star. But then at some point, the low mass star will move in front of the high mass star, and then the intensity will dip a little bit because you're still getting the full the maximum possible intensity from the small mass star, from the smaller star, but it's going to be blocking some of the light that you were initially getting from the larger star, and so you get a small dip. The reason it's a small dip is that the small star is only blocking a small amount of the large star's light. Okay. Then that star emerges, is no longer blocking the big star, and then your intensity goes back up to the full, maximum intensity. But then eventually, the small star will move behind the large star, and now you get a larger dip because you're losing all of the small star's light. Okay. When the small star was in front of the big star, you were only losing part of the big star's light. Some of the big star's light still got through. A lot of it did. But when the small star moves behind the big star, you're losing all of that light. None of it gets through the big star, and so the intensity drops further. And then eventually, obviously, the small star emerges from behind the big star, and the intensity comes up again. And so, fortunately, we have our technology is such that we can actually measure intensity as a function of time for binary star systems like this, and by observing this periodic variation in the intensity, we can conclude that this is a binary star system. So in fact, there are lots of binary star systems that are not visual binaries, so we can't observe, even with our best telescopes, we look at them and we see one point of light, so we can't tell that there are multiple stars there. However, when we follow the intensity over time, we see variations that look like this. And so even though we can't visually tell that there are two stars, we can infer there must be two stars because of the variation in the intensity here. And so in that case, we would have a case of an eclipsing binary, which is not a visual binary. But importantly, they can be the same. You can have a binary star system that is a visual binary that is also an eclipsing binary, right? So these are not mutually exclusive types of binary star systems, but they are different. They're different things, and both useful because they're both things that we observe. So, not to answer the question before asking it, but can an eclipsing binary star system also be a spectroscopic binary? Unfortunately, I didn't actually answer that question for you. So I'll pause here for all of probably 10 seconds or so, and you can always pause me for longer. But think about this. Is it possible? I told you that it was possible to be both an eclipsing binary star system and a visual binary star system. But pause for a little bit and think, is it possible to be an eclipsing binary star system and also be a spectroscopic binary? So I'll pause and let you ponder for a little bit. Okay, so now that you've pondered, let's see. Yeah, probably not surprising. I may have cast a little bit of doubt, but I doubt I was very successful in that. Yeah, it certainly is possible to both be an eclipsing binary and a spectroscopic binary. You know, a spectroscopic binary is just one where you can distinguish between the spectra of these two stars, and by looking at the Doppler shifts of those spectra, you can infer the size, first their velocities, and then from that, combined with Kepler's laws, you can infer the size of the radii. That's a different thing, but it certainly is not mutually exclusive from an eclipsing binary, which again is just a binary star system that happens to have an orbital plane which is oriented relative to us such that one of those stars, that those stars eclipse one another periodically. Okay, so they're just different things. They can certainly coexist and have a single system which happens to be both. So now let's move on and let's discuss how we measure the properties. I mean, we've talked about how we measure the properties of the stars. So now you can imagine that we look out into the cosmos and we make lots of observations of binary star systems. The next question is, what kind of patterns can we observe in the data? Okay. And there are lots of types of patterns one might look for, but there's a particular pattern that has proven to be extremely useful, which was independently observed by a couple of astronomers in 1911, Ejnar Hertzsprung and Henry Norris Russell. And what they plotted, this may not be an obvious thing to you to plot, or it might be, what they plotted was the luminosity of stars versus their temperature. Okay, so by which I mean, and I'll show you an example in just a second, but they put down an XY plot, and they put temperature on the horizontal axis, the x-axis, and they put the star's luminosity on the y-axis. Now, this is not trivial, right, because they're plotting luminosity, not brightness, right? And so what we observe is brightness, as we've talked about it at some length. The luminosity of a star, again, is the total energy that it outputs every second. So that's a function of how far, so luminosity is related to brightness and distance, right? So in order to calculate the luminosity of a star, they had to do some calculations, right? They had to figure out first how far away is the star using parallax, for example, and then, given how bright it is and how far away it is, they could combine those things to calculate the star's luminosity. So they had to do this for each star. They made lots of observations, calculated the luminosity for each star, and it also calculated the temperature by looking at the spectrum and comparing it to the black body spectra of various temperatures. So they say, okay, what temperature black body matches the observed spectrum, and what is its total luminosity? And they put this down on a plot. And in the spirit of continuing our uncreative naming scheme, this plot is now known as the Hertzsprung-Russell diagram, or since Hertzsprung is a complicated name to pronounce too frequently, it's often just denoted the HR diagram. So we're going to talk about this off and on for the rest of the course, but today is our first introduction to it. And you'll see real life examples and you'll see schematics. This is first just a schematic, but it's a great way of introducing it, I think. And this is the HR diagram. Okay, so we've got temperature, as I said, on the horizontal axis, and luminosity on the vertical axis. Now, it's important to make 2 points here. First is that the temperature axis is backwards from anything that you will have ever seen before. So in other words, the temperature is increasing as you move to the left, which is completely non-traditional. The reason for this is entirely because I'm not actually certain of this. My strong suspicion is that when this was originally plotted, it was plotted not with temperature on the horizontal axis, but with wavelength. And we actually will see examples of that as well. Because if you plot this as a function of the wavelength of light, the peak wavelength of light, for example, then it goes in the other direction. And so, and there are cases where they plot it in terms of something called B minus V as well. Which there are various ways of plotting the HR diagram. They all look the same. It's just kind of up to you what you use on the horizontal axis. We will usually use temperature here, but we will see other examples. Anyway, as long as you remember that the temperature is increasing to the left, so it's cooler. These are lower temperatures at the right, and higher temperatures, surface temperatures at the left, you'll be just fine. The other thing to keep in mind is that the luminosity, again, is plotted in log space. And so you very likely have not seen a plot that's quite like this before. What I mean by that is that you see these equally spaced hash marks here. Every time you move from one mark to the next, the luminosity increases by a factor of 10. So, you're getting, if you go from 10 to the minus 1 up to 1, the luminosity has multiplied itself by 10, and multiplies itself by 10 again as you move up to the next mark, and 10 again. And so as a result, we're going from 10 to the minus 5 down here up to 10 to the 7 here. So that's 12 orders of magnitude. That means that the star that was all the way up at the top is 10 to the 12 times larger or more luminous than a star at the very bottom. That's 1 with 12 zeros. Really, enormous. So this is a huge range in terms of luminosity. But there are a couple of things to point out first. So this is the HR diagram again, and you see the first thing that jumps out is that most stars fall along this curve that moves, through the center of the diagram. Not very creatively, that is named the main sequence. And the sun is a main sequence star. It lives right around here. It's the temperature, as I mentioned before, is about 5,800 Kelvin, so just a little bit less than 6,000 Kelvin. And the luminosity here is 1 because, as we very often do, we plot the HR diagram in units of the sun's luminosity. So 10 to the 1 would just mean something that was 10 times as luminous as the sun. 10 to the minus 1 would mean something that was 1/10 as luminous as the sun, and so on. But while most stars are in the main sequence, there are some notable examples. Excuse me. So first, above the main sequence, there are collections of stars which are known as giants. And the reason they're known as giants is that they're much, much larger than a main sequence star of the same temperature. So if we look at, these giants here, they have the same surface temperature as a star down here on the main sequence, but they're much more luminous. They have 1,000 times or even 100,000 times more luminous. So the question is, how could that be? How can they have the same temperature as a main sequence star, as the sun, say, but be 100,000 times more luminous? Well, the only way is if they have 100,000 times the surface area. But that means they're huge compared to the sun. Huge compared to a main sequence star. So that's why they're called giants. It's not creative again. It is what it is. So we're going to have to try to understand, why is it that most stars in the universe fall in the main sequence, but then some, are huge compared to the standard stars, if you will. And there are giants, there are what we call normal giants, and then there are stars we call supergiants, which are even more stupendously large. Most giants and supergiants are red, but some are blue. Okay, so we'll need to try to understand that going forward. And then in addition, there is another class of stars which are known as white dwarfs, which lie well below the main sequence. They are less luminous than main sequence stars of the same temperature, but they're quite hot in general. They're up here, certainly, between at least say 15,000 Kelvin and up towards 30,000 Kelvin. So the question then is, well, how can they be so hot but have such low luminosities? And it's exactly the inverse situation to the giants. The answer is they have to be really small, okay? Because we know they're really hot, which means that their flux is huge. And so if their flux is huge, the energy radiated per square meter is huge, but their total luminosity is small, well, that means they have to be really, really small things. So the question is, how is this possible? Why would some stars be so much smaller than others? So it's a very useful diagram because it takes a stellar census. All of the stars in the universe that we can observe, we can plot them on the HR diagram, and we find that most fall in this very pretty predictable pattern, but some don't. And so a lot of what we're going to spend the next several weeks on is trying to understand and figure out, first, why do most stars fall on the main sequence, and secondly, why do some not? Okay, and how can we maybe predict whether a star will or will not, or determine where it's going to be on the HR diagram. So I've mentioned before the classification of spectral types, and here I just kind of put it up here. M5 is the coolest sort of star, which down here. Turns out there are a lot of those in the universe, and I'll say this again, but there are a lot more cool stars in the universe than there are hot stars. And that's kind of represented schematically here. You see more red dots here than you do more, and those red dots are smaller. Those stars are smaller. There are fewer but more massive, larger blue stars up in, to the hottest class of stars, the O5, for example here. And again, so the goal is to understand why do these stars fall as they do on the HR diagram. And how can we understand, sort of the developments of these stars through their life cycle. The other thing that I would point out is that the size of these stars varies a lot. Okay, obviously I've indicated that when I talk about classes of stars called giants and dwarfs, but to give you a sense of what the order of magnitude of those variations are, you see white dwarfs vary a little bit, but most white dwarfs are really darn close to about 1/100th the sun's radius. Okay, so in terms of radius, they're about 1/100th of the sun's radius. That means in terms of volume, that they're about 1/100 cubed, which is about 1/1,000th, the size of the sun. So which means they're basically the size of the Earth, if you remember. You could fit about 1,000,000 Earths into the sun. So a white dwarf is very similar in size to the Earth. So that's kind of, it's, again, something we're going to have to try to understand. On the other end, if we look at the giants and the supergiants, there are supergiants that are more than 1,000 times larger in radius than the sun. So, again, that means you could fit 1,000,000 suns into one of these supergiants. And so, so it's pretty exciting to see that the HR diagram exists, that there is some order to the madness in terms of the stellar census, if you will. But obviously, as any time you find a pattern, if there are exceptions to that pattern, then the question is, well, why the exception? So again, that's going to be one of our goals over the next several weeks, is to understand why the HR diagram is what it is. So very often when I show you schematics, I'm forced to draw things not to scale because the universe is hard to scale down in a lot of ways. But this is kind of a nice slide because things are to scale, and it gives you a sense of, as we go up from M-class stars, which are again the coolest end of the spectrum, up to O-class stars, the hottest end of the stellar spectrum. how big, how much bigger the O class stars are than the M class. And of course, if you try to put the Earth, on here somewhere, you wouldn't see it. But the Sun is a G class star, so this is kind of where the Sun is. And you can see M class stars are noticeably smaller. And the largest stars, the hottest stars, are much larger in general. And so there just is a lot of variation in the universe. But again, there are a lot more of these low mass, sort of small stars, and many fewer of these large stars. And this again, we're going to revisit the HR diagram over and over again. So hopefully it'll sink in and you'll learn to love it. One other thing to mention, though, I've mentioned that some stars are high density, some stars are low density, and so just knowing the size of the star does not tell you its mass. But on the main sequence, they're directly correlated. And so on the main sequence, as you go from the M class star up to O class star, the mass increases. And so just as the arrow indicates, mass increases as you go from lower right up to upper left. And the more massive the star gets, the hotter it gets. And as we talk over the next few weeks about stellar formation and evolution, we'll understand why that is. And so, sort of the upshot of this observation that Hertzsprung and Russell made, and something that's going to drive a lot of our investigation over the weeks to come, is that almost everything about a star's properties are determined by its mass. So the amount of mass that a star has, when the star's on the main sequence, it determines its temperature, it determines its radius, and it determines its luminosity. So basically any observable quantity related to a star is determined by its mass. And so if you tell me the mass of a star, I can, and you tell me it's on the main sequence, I can tell you how hot it's going to be, how big it's going to be, and how much energy it's going to radiate into space. And to kind of summarize that connection, when a main sequence star is less massive, it's going to be smaller, which kind of makes sense. It's going to be cooler, okay? It's going to have less stuff to burn, less nuclear fuel, so it's going to produce less energy. It's going to be redder, okay? Which, again, we think about red hot, but remember, when it comes to stars, when it comes to physics, red is the cool end of the spectrum, okay? It's the low energy end of the spectrum. And these stars are going to be, less massive stars are going to be less luminous. They're going to give off less energy into space. On the flip side, when a main sequence star is more massive, it's going to be larger, just physically bigger. It's going to be hotter. It's going to be bluer, and it's going to be more luminous. Okay, so by this point, this may not be a surprise, but this is a great summary and certainly something to commit to memory as you work through the homework problems and things like that. I think this will sort of become intuitive, but certainly this is the state of affairs on the main sequence. Again, because as I said, I have to make that caveat because we're going to have to do some investigation to understand why are these other stars, why do they exist, given how most of the stars in the universe fall on the main sequence, why are there exceptions? So we're going to have to talk about them separately. And so, I told you that you would see some schematics of the HR diagram and some real data. Well, this is a real life HR diagram plotted with real stellar data. You'll see here on the vertical axis it is luminosity plotted in units of the sun's luminosity, again, as is typical. As I mentioned, the horizontal axis here is different. It's not than temperature. It's not temperature. It's something called the B minus V color, which is, it's something you can look up on Wikipedia if you want. I don't want to focus on the details there. But you can think of it as temperature. It's sort of related to temperature. And you can see there's no doubt there's a main sequence. This curve is very, very clearly defined. But then you very clearly see this cluster of white dwarfs here that is well away from the main sequence. And then you see certainly these giants up here as well. And one thing that jumps out here is that there's a big separation between the main sequence and the white dwarfs. There's, the white dwarfs are kind of an island unto themselves down here. It's less that way when you think about the giants. There certainly you see the clustering along the main sequence, and you see the clustering along, particularly this region here of giants. But you see there's kind of a scattering of stars in the HR diagram all the way up here. So there's a lot of variation among the giants, but there's a lot to unpack there, as you might expect. So that really is going to be one of the main tasks that we're going to sort of direct ourselves towards over the next several weeks. And I think it'll be interesting. I think it's interesting. Hopefully I'll convince you that it's interesting if you're not already convinced. So anyway, that's the end of this lecture. And so I appreciate your attention. I hope now that you've seen the HR diagram, you'll see it many more times over the coming weeks. So don't skip over that if you were inclined to. But hope you've enjoyed it. Again, thanks for your attention. And I will look forward to seeing you back for Lecture 13.